In 1944, B-29 crews feared their own engines more than enemy fighters. The Wright R-3350 was supposed to power America's ultimate weapon, but engine fires could burn at 5,600 degrees Fahrenheit and melt through the main wing spar in seconds. What turned the most powerful engine of World War II into a mechanical nightmare that nearly grounded the mission to end the war? When preliminary designs were presented in mid-1940s for a long-range bomber capable of flying from the U.S. to Germany with 20,000 pounds of bombs, 3 of the 4 designs used the R-3350. The Pacific War demanded something unprecedented, a bomber that could fly farther and higher than anything ever built. The B-29 Superfortress promised the impossible, but it needed an engine to match those dreams. Wright Aeronautical had the answer on paper, but delivering it would become one of aviation's most dangerous gambles. The pressure was immense and the timeline brutal. America's entry into World War II accelerated development schedules that were already pushing the boundaries of 1940s technology. The Army Air Forces needed a strategic bomber capable of reaching targets 3,000 miles away while carrying massive bomb loads at altitudes above 30,000 feet. No existing engine could meet these requirements, forcing Wright to essentially create an entirely new class of aircraft engine. The engineering challenges were staggering, managing the power output equivalent to a small power plant while keeping weight low enough for flight, all while operating reliably in combat conditions that would test every component to its breaking point. The stakes couldn't have been higher, as the success or failure of America's strategic bombing campaign would ultimately depend on whether Wright could deliver on their ambitious promises. The Wright R-3350 Duplex Cyclone wasn't just an engine, it was controlled thunder wrapped in aluminum and steel. This American twin-row, supercharged, air-cooled radial aircraft engine featured 18 cylinders, displacing nearly 3,350 cubic inches. Power ranged from 2,200 to 3,700 horsepower, depending on model, making it one of the most powerful radial engines ever built. When the Duplex Cyclone roared to life, it generated more raw power than any radial engine before it. Twin rows of 9 cylinders each breathed through General Electric turbo superchargers that force-fed compressed air into hungry combustion chambers. This was the engine designed to be the heart of America's strategic bombing campaign, powering the B-29 Superfortress, consolidated B-32 Dominator, and later the Lockheed Constellation airliner. The physical dimensions were staggering for its era. Standing 55 inches high and 76 inches wide, the R-3350 had a dry weight of 2,595 pounds, making it both the largest and heaviest radial engine ever installed in a production aircraft. Each cylinder was larger than those found in many automobile engines of the period, and the total displacement exceeded that of many marine engines. The supercharger system alone represented cutting-edge technology, using exhaust-driven turbines to maintain sea-level power output at altitudes where the air was too thin for conventional engines to function. Wright Aeronautical Division would produce thousands of these mechanical giants between 1940 and 1960, but the path to that success would be paved with tragedy, innovation, and an engineering learning curve measured in lives rather than test hours. If you're fascinated by stories of engineering pushed to its absolute limits, subscribe now. We've got more legendary machines that danced on the edge of disaster. The first R3350 was run in May 1937, but continued development was slow due to the engine's complex nature and Wright's focus on the smaller R2600. The R3350 didn't fly until 1941 in the prototype Douglas XB-19. What appeared to be thorough development actually masked fundamental problems that wouldn't surface until the engine faced combat conditions. Development and early application was particularly troubled by catastrophic backfires. Engineers struggled with the complexity of managing 18 cylinders arranged in twin rows, each requiring precise fuel metering and cooling. The engine's enormous displacement created heat loads that conventional cooling systems couldn't handle, but the pressure to deliver a combat-ready engine meant that these issues were pushed aside. Racing against time as America entered the war, Wright found themselves caught between engineering perfection and military necessity. Altogether, the R3350 went through tens of thousands of design changes during its early development. Each modification attempted to solve cooling problems, fuel distribution issues, and mechanical failures, but the fundamental challenge remained. Wright had created an engine that generated more heat than it could safely dissipate. The engineering complexity was unprecedented for its time. Managing fuel flow to 18 individual cylinders required sophisticated carburetor systems that often delivered uneven mixtures, creating hotspots that could trigger detonation or pre-ignition. The twin-row configuration meant that the rear cylinders were partially shielded from cooling airflow by the front row, creating a thermal management nightmare that would plague the engine throughout its early service life. Test pilots reported engines that would run smoothly on the ground but developed serious problems under the high-power, high-altitude conditions required for combat operations. Wright's engineers worked around the clock to solve these issues, but the compressed development timeline meant that many problems were discovered only after engines had been delivered to operational units, turning combat crews into unwilling test pilots for an unproven engine. Enjoying this story of engineering under extreme pressure? Hit subscribe so you don't miss the next forgotten engine that changed the world. By 1943, the Boeing B-29 Superfortress, powered by the R3350, was flying. However, the engines remained temperamental and showed an alarming tendency for the rear cylinders to overheat. A number of changes were introduced into the aircraft production line to provide more cooling at low speeds, with the aircraft rushed into operational use in the Pacific in 1944. When B-29s finally reached combat operations, the sheer scale of their mission was unprecedented. These bombers could fly farther than any aircraft before them, carrying massive bomb loads to targets deep in Japanese territory. The R-3350 enabled missions that would have been impossible with any other engine, reaching altitudes where the turbo superchargers gave American bombers a crucial advantage over enemy interceptors. Despite their problems, R-3350-powered B-29s began demonstrating their strategic value. The engines could maintain power at altitudes exceeding 30,000 feet, allowing bombers to operate above most Japanese fighters while carrying devastating payloads. When the engines functioned properly, they delivered exactly the performance Wright had promised: unprecedented range and power that could project American air power across the vast Pacific. The operational capabilities were genuinely revolutionary when everything worked correctly. B-29s could cruise at 350 miles per hour at 25,000 feet while carrying 10,000 pounds of bombs over distances exceeding 3,000 miles. Performance levels that represented a quantum leap beyond any previous bomber design. The pressurized cockpits allowed crews to operate in shirt sleeves at altitudes where other bombers required bulky oxygen equipment and heated suits. The centralized fire control system, powered by the engine-driven electrical generators, enabled defensive firepower that could theoretically engage multiple attackers simultaneously. These technical achievements validated the strategic vision beyond the B-29 program, proving that long-range precision bombing can reach any target on Earth when the engines performed as designed. The psychological impact on Japanese defenders was immediate and profound, as they realized that their homeland was no longer protected by the vast Pacific distances that had once seemed insurmountable. But behind the strategic success lay a hidden danger that threatened the entire B-29 program. Because of a high magnesium content in the crankcase, engine fires could burn with a core temperature approaching 5,600 degrees Fahrenheit, which could burn through the main spar in seconds, causing catastrophic failure. This was the R-3350's most terrifying secret. When things went wrong, they went wrong fast and fatally. The early B-29s taking off at maximum weights in the high-temperature conditions of tropical airfields caused overheating that was never completely solved, and the engines developed a tendency to swallow valves. Combat crews discovered that their most dangerous enemy wasn't Japanese fighters, it was their own engines. More B-29s were lost to mechanical failures than to enemy action during the initial raids on Japan. The magnesium components, chosen for their light weight, became death traps at high temperatures. Unlike conventional aluminum fires that could be fought with standard extinguishing systems, magnesium fires burned so intensely that they could consume critical aircraft structures before crews had time to react. Early R-3350s used carburetors with poorly designed elbow entrances to the supercharger that led to serious problems with fuel and air mixtures, creating hotspots that could trigger catastrophic failures. The statistics were damning and carefully concealed from the public. Of the 414 B-29s lost during the bombing campaign against Japan, 147 were destroyed by enemy flak and fighters, while 267 were lost to engine fires, mechanical failures, takeoff crashes, and other operational causes. In 87% of engine fires, the onboard extinguishing systems proved completely inadequate against the magnesium blazes. During the first 6 months of B-29 operations, 10% of bombers taking off would be lost to mechanical defects alone on every mission, a casualty rate that would have been considered unacceptable in any other military operation. Crews developed gallows humor about being killed more by Curtiss Wright, the parent company of Wright Aeronautical, than by the Japanese. The magnesium crankcase would burn with such intensity that it could melt through wing spars in under 30 seconds, giving crews virtually no time to bail out once an engine fire began. These weren't isolated incidents, but systemic failures that threatened to ground the entire strategic bombing campaign against Japan. Salvation came not from Wright's corporate headquarters, but from desperate mechanics and engineers working in Pacific theater maintenance units. These men, watching their friends die from engine failures, began developing unauthorized modifications that actually worked. Field crews created new cooling baffle designs, modified operating procedures that kept engine temperatures within survivable ranges, and developed maintenance protocols that could predict failures before they became catastrophic. The breakthrough came when Wright finally implemented a comprehensive redesign program, incorporating lessons learned from both combat failures and field modifications. Improvements were made to reduce overheating, including changing from a downdraft carbureted system to fuel injection, which eliminated inconsistent fuel and air distribution. Pilots learned to use as much of the runway as possible and build up speed to help cool the engines before slowly climbing for altitude. As design problems were overcome, R3350 saw its time between overhauls increase from 100 to 400 hours by the end of the war. By late 1944, the R3350 had been transformed from a liability into a reliable weapon. The Duplex Cyclone finally became the engine Wright had promised, a powerhouse capable of carrying the war to Japan's doorstep. The field modifications were ingenious and born from pure necessity. Mechanics developed propeller cuffs that directed additional cooling air into engine intakes, while new baffles channeled airflow directly onto the problematic exhaust valves. Oil flow to the critical valve mechanisms was increased, and asbestos shields were installed around rubber components to prevent oil loss during high-temperature operations. Perhaps most importantly, maintenance crews established aggressive inspection schedules that required replacing the 5 uppermost cylinders every 25 hours of engine time and complete engine changes every 75 hours. Maintenance intervals that would have been considered impossibly short in peacetime were proved essential for preventing catastrophic failures. Flight crews developed new operational techniques, using maximum runway length to build up airspeed before liftoff, which provided additional cooling airflow during the critical climb phase. Engine management procedures evolved to balance power settings carefully, avoiding the temperature spikes that could trigger the cascade of failures leading to fires. These innovations, developed through trial and error in combat conditions, ultimately saved both the B-29 program and countless aircrew lives. The redeemed R3350 powered the bombers that carried out the most devastating air campaign in history. From the Great Fire raids that burned Japanese cities to the atomic missions over Hiroshima and Nagasaki, the Duplex Cyclone finally delivered on its promise to end the war from the air. After the war, the engine was redesigned and became a favorite for large aircraft, notably the Lockheed Constellation, Douglas DC-7, and Lockheed P-2V7. Wright was the only aircraft engine manufacturer to put a turbo compound engine into production, with the first production turbo compound R3350s delivered in March 1950. These post-war versions represented the pinnacle of piston engine development, using exhaust-driven turbines to extract additional power from waste gases. Turbo compounding added about 550 horsepower at takeoff and 240 horsepower at cruise settings over similar non-turbo compounded engines. By this point, reliability had improved dramatically, with mean time between overhauls reaching 3,500 hours and specific fuel consumption achieving 0.4 pounds per horsepower per hour, giving it 34% fuel efficiency. The engine powered the golden age of propeller-driven airliners, proving that lessons learned from the R3350's troubled early years had created something truly exceptional. Even today, the engine is commonly used on Hawker Sea Fury and Grumman F8F Bearcat Unlimited class racers at the Reno Air Races. The post-war turbo compound development represented a technological triumph that vindicated Wright's original engineering vision. 3 power recovery turbines, PRTs, were positioned at 120-degree intervals around the rear of the engine, each driven by exhaust gases from 6 cylinders. These turbines transferred recovered energy back to the crankshaft through fluid couplings, essentially extracting usable power from what had previously been waste heat. The system operated automatically without pilot intervention, adding only 11 inches to the engine's overall length while contributing substantial power increases. Commercial airlines embraced these engines for their exceptional fuel efficiency and reliability, with some turbo compound R3350s achieving cruise fuel consumption rates comparable to much smaller engines. The technology proved so successful that Wright planned even more advanced versions, incorporating turbo supercharging for high-altitude operations, though these developments were curtailed by the advent of jet propulsion. The R3350's post-war success in civilian aviation demonstrated how wartime engineering challenges, once overcome through persistent effort and real-world testing, could yield innovations that benefited both military and commercial applications for decades to come. The Wright R3350 teaches us that true engineering legends aren't born perfect. They're forged through failure, refined by disaster, and ultimately proven by those brave enough to trust their lives to the result. The engine's journey from death trap to triumph illustrates how persistent engineering effort can overcome even fundamental design flaws when guided by real-world experience and honest confrontation with problems. The mechanics and engineers who refused to accept the engine's early failures created solutions that not only saved lives, but established principles that influenced piston engine design for decades. The R3350 story reveals both the promises and perils of pushing technology to its limits under wartime pressure, demonstrating how even fundamentally sound engineering concepts can become dangerous when insufficient time is allowed for proper development and testing. If you love the story of mechanical redemption and engineering perseverance, hit that like button and subscribe. What legendary engine should we explore next? The troubled Allison V1710 that powered the P-40, or the record-breaking Pratt & Whitney R3350 that dominated the post-war skies? Let us know in the comments which aviation legend you want to hear roar again.